So this is section 17.7, and I said this is the last section. It is a continuation of the previous section where we talked about KSP. By the way, this is slide 105 in your lecture notes. We are going to talk about the common ion effect, if you remember from the buffer section, and the effect of pH on solubility. You've done an experiment when you did the Le Chatelier's principle and you tested this. So the theory is not new to you, but we are going to look at it from a solubility perspective. Okay, the common ion effect on solubility. So what is the common ion effect? If you remember, I'm trying to get everything in here. If I have a weak acid, I'm going to talk to you with regard to the buffer system and what we understood at that time about the common ion effect. So you have a weak acid, and it dissociates to give A minus, the conjugate base, and H3O plus. Now when I add more A minus from an external source, okay, so you had a problem in your homework, I believe. The formate ion, you can add sodium formate or potassium formate. All you're looking for is some extra formate in the system. So when you add more A minus, this concentration increases. Okay, this increases, and what does it do? It shifts the equilibrium to the left. That in essence is the common ion effect. You may want to go back to the slides from the beginning of this chapter where we talked about the common ion effect. I think that was the first section, and we talked about an example like that, and we also did calculations to see how the equilibrium is shifted to the left. So the common ion effect is the suppression of a weak electrolyte's ionization. Okay, suppression of a weak electrolyte or a weak acid or a weak base in the presence of a strong electrolyte containing an ion common with the weak electrolyte. I'm trying not to move this. Okay, containing an ion that is common with the weak electrolyte. So you're adding from an external source. So you can add sodium acetate, for example, or sodium formate. This is a strong electrolyte, but it produces the ion that comes from the weak electrolyte here. You understand the statement? So you're adding more of the A minus, which is the conjugate base of this weak electrolyte. And how do you add more of the A minus? More A minus is going to come from adding a strong electrolyte that contains A minus. Okay, so you need to understand the dynamics of this even to understand buffer action. Now here we are going to talk not about a weak acid or a weak base, but still a weak electrolyte. AgCl, if you look in your solubility chart, This is considered to be sparingly soluble, or your solubility chart will say that it's insoluble. So this is a weak electrolyte here. All right, so the common ion effect works for any weak electrolyte. It could be a sparingly soluble ionic compound, or it can be a weak acid or a weak base. Okay, solid, and this is in equilibrium with Ag plus ions and Cl minus ions.
Back for more fun tomorrow.
Okay, bye, Dr. Dees. You too. All right, it's Dr. Dees leaving, and it's 7:22 p.m. here at school. Well, AgCl is now in equilibrium with few of its Ag plus ions and Cl minus ions. Okay, and they say the value of X, remember the molar solubility of AgCl is this 1.33 times 10 to the negative 5. Now the question is this: you're going to add of the two ions. Okay, they've picked Cl minus to be the common ion. Now how are you increasing? Okay, how are you going to increase the concentration of Cl minus? Okay, how are you going to increase the concentration of Cl minus? You want to increase the concentration of one of the ions. They picked Cl minus, so how are you going to do that? You're going to add 0.200 molar NaCl. So this is your strong electrolyte that produces Cl minus ions in solution. Okay, I'm actually using this topic to clarify what you've learned about the common ion effect in the buffer section. So when you increase the amount of Cl minus here, okay, increase the amount, additional Cl minus shifts the equilibrium too. So think about it. You have this perfect equilibrium. You're going to apply a stress. Remember Le Chatelier's principle. How are you applying the stress? You're increasing the concentration of Cl minus. And how are you adding extra Cl minus? By adding 0.200 molar NaCl. Okay, so when you add that, this increases. So your Q, remember, Q is going to increase, and therefore to make Q equal to Ksp, remember all that, it's going to shift the equilibrium to the left. Shifts the equilibrium to the left, and products convert to reactants. All right, products convert to reactants. Does it make more sense? That's the common ion effect. So your weak electrolyte can be a weak acid, a weak base, or a sparingly soluble ionic compound. And you can test it with any of these, but the result is the same when you increase the concentration of the, see, this ion is common with this ion. That's why it's called the common ion effect. So if you add more of this, then it's going to shift to the left. Next slide. I have 107. Now we're going to demonstrate this using a problem. This will make more sense to you when I do this, I think. I'm not able to shrink this anymore, and it's huge. So anyway, I'll fix it for the next one, I suppose. This is the max zoom that I have here. Okay, sorry about that. So let's start. We're going to do an ice table just like we did in section 7.1. We're going to test the common ion effect, AgCl, solid, Ag plus Aq. This is a simple equation because the ratio is just 1 to 1 and the charges are simple. Now you may want to have your notes with you in case you're not able to see the whole slide. So initially, remember, this is the solid, so it's an excess minus x. Initially this is 0, 0 plus x plus x. Now let's read the problem again. Calculate the molar solubility of AgCl in a solution of 0.200 molar NaCl. Okay, so I'm going to move it to the side. They're adding NaCl and it's going to completely dissociate to give Na plus and Cl minus. Of course, all are Aq. This is a strong electrolyte. And this is 0.200 molar. At the end you have 0, and this is 0.200 molar and 0.200 molar of the Cl minus. Okay, so initially from the external source, okay, so this is your external source, you're adding 0.200 molar of Cl minus. So remember, if you have the common ion, we do that. Draw a line to separate the two. Okay. Now, at equilibrium, you see what's happening? You're adding sodium chloride to produce more of the common ion. Okay. This ion comes from sodium chloride. This ion also comes from AgCl. So it's a common ion. And so in the equilibrium, because you're adding this, there's an excess amount of the chloride. So remember, we don't put anything there because it's a solid. This is x, and this is 0.200 plus x. Okay. Now, the molar solubility is given. Okay, let's write the expression for Ksp. So this is x and 0.200 plus x. Now I'm going to find the value of Ksp for you from the table. Ksp is 1177 times 10 to the negative 10. Okay, you should be able to find this in the tables that we were looking at. That's in your notes. Now, because this Ksp is so small, remember, we can make that assumption. Now solve for x. I'm going to let you solve for x. I have the value here, and this is 8.85 times 10 to the negative 10 molar. Okay, and this is the molar solubility. Okay, look in your notes from today, this afternoon. Molar solubility of AgCl. This is actually the amount of the cation that goes into solution. Okay, that's what we call as the molar solubility. So the value of X when you have added the common ion is 8.85 times 10 to the negative 10. Now, I'm going to add another sheet. Let's read the problem again. What is the molar solubility of AgCl? Okay, let's read it here. Calculate the molar solubility of AgCl in a solution of 0.200 molar NaCl. In a solution of 0.200 molar NaCl. Got that? And this is the X that you calculated, which is 8.85 times 10 to the negative 5 molar. So you had the common ion. All right. So you have AgCl, solid. So you can understand I'm just going to give you the initial values. This is excess. 0. This is 0 plus. Okay. We have the common ion 0.200 molar. And then you did the change, minus X. You may be wondering why I'm writing this. I'll let you know. Okay. Common ion. Okay, common ion effect. You got that? So this is a summary of the calculations from the previous slide. You set this table up. You had the common ion included, and you calculated X, and X from this calculation was 8.85 times 10 to the negative 5. Got that? Now, they're saying compare it. Okay, you can freeze the slide and look at it again if you need to. Molar solubility of AgCl in pure water. Okay. Now the 0.200 molar, that's so many moles in 1 liter. So they may be doing the experiment in 1 liter. So you can say they have 1 liter of pure water. This calculation was already done. And I'm going to show you how they would have done it, because you may be asked to show that as well. I'm going to do the I and the C nice part. So excess minus X, 0. There's no common ion, okay? No common ion. Plus X. Plus X, 0 plus X. There's no common ion. You see that? There's no common ion. In fact, I should have called it Y just to make it stand out from the previous X. Okay, so this is just X. And they calculate this X, which you can do from the KSP value. Probably you should try it. And the X value, they've given it to you in the problem. Read the problem again. Molar solubility of AgCl in pure water is what? 1.33 times 10 to the negative 5 molar.